Hi guys, I hope you had a really awesome snow day. I want to finish up chapter 6, so we're going to cover just a little bit more of 6.3, and then we're also going to cover all of 6.4. You are probably going to hear some Christmas music in the background because it's Breakfast with Santa. I've tried to drown out as much of it as I can, as you can see over here. Just trying to drown out the speaker right now for you, but I couldn't probably get it all of the way. So I apologize that you're also being serenaded a little bit in the background. So just kind of work with me. Hopefully you'll be able to hear everything I think that we need to hear. Okay, so I think the last place that we left off was with centrifugal force. And remember we said that centrifugal force is actually a fictitious force. And the difference between a real force and a centrifugal force is that a real force is something that's happening because of an interaction between two objects. So I have two things that are happening, and that should be following Newton's third law, which is that for every action, you're going to have an equal but opposite reaction. So centrifugal forces are different. A fictitious force is different because it's only acting on one thing, and it's not having some type of interaction or a reaction back to it. So we call these fictitious forces because we feel them, we experience them. So in our minds, we're thinking that a force is actually happening when in actuality, it's not. So for example, for centrifugal force, when you are negotiating a curve, we know that there's a force that's appearing to push us towards one side of the door. It's like that door that's kind of stopping us. But this is our fictitious force. So we feel like this outward kind of pull almost when we're negotiating a curve. So we can see that here. This would be what we would call centrifugal force. And that's a fictitious force. That's not actually what's happening. Instead, we have friction that's keeping us in that car, continuing to negotiate that curve. So this is the real force that's acting. So centrifugal force, fictitious force, friction is the real force that would be keeping us in the car as we're negotiating a curve. If we also look at, I think it's this one. Yeah, so here's another just example of centrifugal force. So let's watch this.
As the turntable spins, the tension in the string supplies the centripetal force that holds the disc in uniform circular motion. Like any object in uniform circular motion, the disc is accelerating. If we mount the camera on the disc, we are in an accelerating reference frame, and the disc appears to stand still. When we break the connection, the disc is seen to accelerate outward in this frame. If we try to use Newton's second law to explain this motion, we must introduce a fictitious force to explain the observed acceleration. This is the so-called centrifugal force. In a non-accelerating frame, the disc is seen to obey Newton's first law. When the connection breaks, the disc does not accelerate, but continues to move in a straight line and at constant speed. The so-called centrifugal force is not a real force. It only appears to exist in a rotating reference frame.
Okay, so in that example, you could see that when that whole turntable was moving around, when we were in that accelerated frame, it looked as though that disc wasn't traveling that straight path. And that's what we actually observe most frequently when we're thinking about things in accelerated reference frames. It looks like they're disobeying Newton's first law, where that it's going to continue to move in that straight line until another force acts upon it. And it truly does. It's just that because we're observing something in an accelerated reference frame that it looks different to us. Another example of a fictitious force is something that's called the Coriolis force. We oftentimes think about this if we're on like a little merry-go-round, a carousel, something like that. So let's say that you were on this merry-go-round and you were trying to pass a ball to your friend that is on the exact opposite side of that merry-go-round from you. Let's see what happens in that case. So let's say that we have two different views of this. We can think about maybe what we're observing from two different reference frames. So I'm going to have this thrown, and I'll do this a couple times so you can see this. Let's watch this one first. This is what we would be observing with respect to the Earth. So this is the view according to an observer fixed with respect to the Earth. So we're going to throw this. My eye was right here, and as that merry-go-round is moving, I'm going to pass that ball, but I'm no longer here because I'm moving also with this merry-go-round. So if I'm an observer on Earth, just respect to the Earth, I'm seeing that this ball is just traveling in a straight line. It's just that my position is different and my friend's position is different now. But what would happen, or what do we observe if we are actually an observer with respect to that rotating platform? What do we see? So now let's watch this one here. Okay, so in this case, if I'm thinking about being on the platform, I know the platform is moving, and in this case, since I'm an observer on this platform, I'm not thinking about my change in position, I'm just going to watch that ball move. For me, if I'm standing on that platform, now it looks as though the ball isn't moving in this straight path, instead it has this curvature to it. So again, let's go back and watch this one. So this would be with respect to the Earth. So because we're moving on this platform, the ball does move in this straight line. It's just that because I am moving with this platform, that now my position has changed, so I'm not going to be able to catch that ball. In this case, if I'm thinking about myself on the platform, accelerating with that platform, and I'm not thinking about how my position is going to be changing, I'm assuming that that ball should come straight to me, but instead I'm seeing that it's going to have this curved effect, which we call this a fictitious force because we know that it should obey Newton's first law, that it's going to continue to travel in this straight path. But what we experience is that there's this fictitious force or a fictitious effect. We call that the Coriolis force or Coriolis effect. So that's another type of fictitious force. But we know that that's not true. It's fictitious. So guys, starting section 6.4 is all about dealing with motion with resistive forces. So when we have to think about things in terms of moving in a medium. I know oftentimes we just kind of ignore the fact that things are moving in a medium, or we ignore a possible resistance to what the object is moving through. But now we don't want to ignore that necessarily anymore. We know that the magnitude of the resistive force, or actually let's just say we are going to symbolize resistive force with a capital R, and that's going to be for an object moving through a medium. Typically we're going to think about these mediums as being gases or being a liquid. So the magnitude of R is going to depend on the medium. The magnitude of R depends on the medium. The direction of R is going to be opposite the direction of motion that of the object relative to the medium. So the direction of R is opposite the direction of motion of the object relative to the medium. Let me say it one more time. The direction of R is opposite the direction of motion of the object relative to the medium. Okay? So the magnitude of R can depend on speed in very complex ways. We are going to talk about two particular ways that magnitude and speed can have a relationship. The first one that we're going to talk about is when the resistive force is proportional to V, when it's proportional to speed. And this would be a good approximation for very slow motions, so this is a good approximation for slow motion, or for very small objects. So when we have resistive force being proportional to speed, it's only when we have slow motions and when we're also thinking about small objects. Another type of way that resistive force can depend on speed would be when the resistive force is proportional to the square of the speed. And in this case, this would be a good approximation for very large objects. So we're going to talk about each of these separately in individual cases. The first one, let's just talk about resistive force being proportional to speed. So the resistive force can be expressed as we have resistive force, and then that's equaling a negative B times V. B is just a variable that's going to depend on several things about the object that we're talking about. So B is going to depend on property of the medium, it's going to depend on the shape of the medium, and also the shape of the object, property of the medium, and then also the dimensions of the object. So this negative sign here is also indicating that R is just opposite in direction of that motion. So it's opposite in direction to V. Okay, if we are taking, for example, maybe that we're going to have just a small sphere, we're going to call it mass M, and we have this small sphere that we're going to release in a liquid. So I have a beaker here, I'm releasing that into a liquid. In this case, I know the forces acting on it, if I draw a free body diagram, are going to be the weight force, so I have that gravitational force, and then I also have the resistive force, which should be acting opposite to the motion, right? Because that small sphere is going to keep going down because gravitational attraction, so the resistive force is going to be working against it. If we think about the forces that are acting then, or if I want to write the sum of the forces in the y direction, because the only forces that I have in play are forces in the y direction. I'm going to take sum of the forces in the y direction is equal to the weight force, mg, minus my, or I could think about it as plus the resistive force, but because it's in opposite direction, I'm going to have mg minus my r. So mg minus bv. Remember that the resistive force is also equal to bv. So the reason that it's mg minus bv is because the motion is directed this way. So because it's moving in this direction, that gravitational attraction, since it's moving with that direction of speed or of velocity, I'm thinking about this then as being that positive direction, okay? So my weight force minus my resistive force is going to equal my net force, mass times acceleration. If I want to think about what the acceleration would be then, so let's go back here, guys, to the Promethean board. We had the sum of the forces. Sum of the forces in the y direction was equal to the weight force minus that resistive force, and that equals my net force, which is mass times acceleration. So if I want to think about what would the acceleration be, how could I get an expression for acceleration? If I do that, I can just divide both sides here by mass, and I would end up getting that acceleration would be equal to g, because the m's here would cancel out. That m still, though, would have to be over that bv, because I don't have anything to cancel out there, so it should be g minus bv over m. So this would be my expression for acceleration if I'm thinking about the resistive force when it's proportional to speed. So this would be a good equation that I may ask you to derive if we're talking about resistive forces being proportional to speed. Okay, so still thinking about resistive forces being proportional to speed. So we know that before we're releasing anything, its initial velocity is going to be 0. So then if its initial velocity is 0, then its before I've applied anything to it, its initial acceleration is just going to be that, I think about it as my little free fall object. So my acceleration would be acceleration due to gravity. When I release that, I know that it's going to, as time starts to increase, I know that my resistive force is going to start to increase. That object is going to be interacting with the medium that it's in contact with, so the resistive force is going to increase. This was one of your objective questions, or maybe it was a conceptual question in your homework, where it asked what happens to acceleration as an object is moving towards terminal velocity or terminal speed. Think about when we're high up in the atmosphere versus when we're lower down in the atmosphere. High up in the atmosphere, we don't have as much matter, and as an object is moving down further closer to Earth, then that medium becomes denser, so it becomes more dense. Because of that, resistive force is increasing. So acceleration can't just stay this constant 9.8 meters per second squared. So as my resistive force is increasing, my acceleration is going to start decreasing. Once that acceleration approaches 0, I know that my resistive force is going to become equal then to the weight force. When that happens at this point, we call the speed then terminal speed. So terminal speed is where we get my weight force to be equivalent then to that resistive force. So, and that would be as that acceleration is then approaching 0, I get resistive force equaling the weight force. That's what gives me my terminal speed. Okay, so if we want to find the terminal speed, then we can think about that as when A is equal to 0. So when we have reached terminal speed, that means that my resistive force is now equal to my weight force, right? And we just said that A was equal to G minus BV over M. We just found an expression for acceleration in terms of when resistive forces are proportional to speed. So specifically, when acceleration is 0, that means we've reached terminal speed. So I'm going to write a little t here by the v to represent that this would be the terminal speed. So when this is 0, let's find an expression for terminal speed. So when this is 0, I want to rearrange this equation so I could get my terminal speed is equal to something. When I do that, if I rearrange all of this, I'm going to get my terminal speed to be equal to mg over b. So my terminal speed can be calculated by taking mg over b. Okay, we can also, if we think about when our time is 0, when our speed is 0, we can also have another equation to help us solve for terminal speed. And this is going to be requiring quite a bit more calculus that I don't think that you have gotten to yet in BC Calc. So I'm going to give you the equation here. Later on, we'll work on using the differential